Hi everyone, my name is Irlango Cheren, and today I'd like to talk to you about lexical data, or dictionary data, and a case study of deriving it for the Tamil language from scratch using morphology. In this talk, I'd like to talk to you about a few things. First, in which ways are lexical data useful for Tamil? And to do that, we would need to describe what the properties of Tamil are that make it a good subject for case study, and also which other languages share this linguistic properties. Then I'd like to tell you about the challenges to finding and using lexical data and describe my resulting approach for bootstrapping the lexical data derivation and also explaining the relationship of some of the steps taken to ICU and CLDR functionality. And then in the end, I would like to discuss some of the implications of the things that I found along the way. How lexical data are useful. The first linguistic aspect of Tamil to discuss is its script. Tamil has its own script, and you can see some examples of letters to the right. There are ik, ka, ka, ke, and ko. The script for Tamil is known as an abugida script, which is also known as an alpha syllabary. And what this means is that a letter is written as a base grapheme with optional combining graphemes. A grapheme is a unit of writing, which means that it's a shape that makes a difference in how we interpret what's written. This is the base grapheme, and it's present in letters that have the same sound. Here are the combining graphemes, also known as combining marks. Now, the graphemes are units of how we write, and so people maintaining coded character sets, like Unicode, will care, as well as people creating fonts and rendering those fonts. But graphemes do not always represent sound. The dot, known as a pulli, which means dot, when placed above the ka, now makes it represent the pure consonant ik. The dot cannot be pronounced, but it is a grapheme. So language speakers read and think in terms of letters of the language. They do not think in terms of graphemes. However, while humans will think of in terms of letters, in a Unicode setting, we can refer to them as grapheme clusters, and at least for abugidas, this is an okay equivalence in terminology. Tamil has 12 vowels. Here are a few. There are 18 consonants, and every pair of consonant and vowel creates a new letter, which adds 216 letters. Languages that use abugida scripts are across the world. In South Asia, most of the languages use abugida scripts, including most of the languages of India. In parts of Southeast Asia, languages such as Thai and Khmer. In peninsular East Africa and the Horn, languages such as Amharic. And in Canada, the Aboriginal languages. By my rough count, there are approximately 1.5 to 2 billion people who speak languages using abugida scripts. Another important aspect of Tamil is its agglutinative morphology. And by morphology, I mean the ways in which words change to convey different meaning. I may use morphology and grammar interchangeably, and for the purposes of this talk, that's okay. Agglutinative languages use suffixes a lot to convey meaning. And by a lot, I mean in comparison to English. So in English, a preposition might be a separate word, but in agglutinative languages, they might be conveyed by adding suffixes. So here we have a verb conjugation. We have the verb irlu, which means to write, and it's shown in green, and it's used in the sentence I write, the present tense. Now first we add a suffix shown in blue that indicates the present tense. After that, we add a suffix shown in red that indicates subject agreement, also known as person, number, gender. And here it's the first person singular, which is the word I in the sentence I write. Now the suffixes get chained together. So also notice that when you have a suffix beginning in a vowel sound being added to the end of something that ends in a consonant, then the consonant and the vowel sound combine to form a new letter. So in purple above, we have the blue pure consonant ir being added to the vowel sound in red, e, to create a new letter in purple, re. Now, we still have the same notion of a word that we do in English, But compared to English, there will be more words and there will be longer words. It's a combinatorial increase because we have to include all the possible suffixes that we can add. So for verb conjugation, for every verb root, we have multiple tenses and we have multiple subject agreement ending suffixes for the person, number, and gender. And then you have to take that number and multiply it by the number of forms of the verbs. So down below, we don't just have the simple present tense, we also have I write myself, which is reflexive, I am writing a continuous, and then there's another verb form called I write, and we'll finish. There's a completion that's indicated. And there are other verb forms as well. And this is true no matter what algorithm we use to compute the boundaries of the words. Agglutinative languages are also spoken across the world. They include languages like Finnish, Hungarian, Turkish, Japanese, and Korean. And they also include a lot of languages of sub-Saharan Africa, South India, parts of Southeast Asia, and the Western Aboriginal languages. By my rough count, there are more than 1 billion speakers of agglutinative languages. Let's look at some potential use cases of lexical data. For spell checking, it might be possible to have a more compact yet thorough dictionary lookup if we store just the word stems. By storing the word stems and not all of the words that we find themselves, it will obviously be a big space savings. But it could also be more thorough because we can generate the verb conjugations and noun inflections using all the word stems. And this might be able to catch some of the words that we might be missing if we're just collecting all the words that we think we know. Stemming is another potential application. Stemming is an important step in a lot of natural language processing programs, for example, sentiment analysis. And the reason why a dictionary is important there is when we see a word, we may not know at first whether it's the inflected form of a noun or the conjugated form of a verb. Indexing is another place where dictionary data could be useful. Now, let's say we're indexing content in order to be matched against a search query. Now, if the search query contains a verb, then maybe that verb should match all of the conjugations of that verb, as opposed to having every single conjugation being treated as a different word and matching independently. Another use case might be having a better autocomplete. Now, this diagram shows a user typing with this input method for Thumber, and they're in the middle of typing a verb conjugation. As you can see, the autocomplete suggestions are too big to fit in the space provided. So in order to make them fit, they remove some content in the middle and provide an ellipsis. But the problem here is that since we're typing in the middle of the word, the part that's being hidden is actually the really relevant part that we want to know. Another problem is that we can see in the auto suggestions, the verb ending suffix does not match the subject of the sentence being written. So basically, what's happening here is something that works quite well for English is breaking down for an agglutinative language. And it's breaking down for the same reasons that we have more and longer words in the agglutinative language. Instead, what we should do is we should suggest one suffix at a time and autocomplete on that. So, for example, in this hypothetical scenario, we could be suggesting first the tense marker suffix, and then after that, we can be suggesting the person, number, gender subject agreement suffix. And there's a user experience problem here, which is that there's a problem that users feel, but how do we get product creators to understand it? Let's talk about some of the challenges to finding and using lexical data. Some of the best existing data sets are actually proprietary. We have some of the highest quality dictionary data, including definitions, examples, parts of speech tagging, and bilingual data. But they've been created primarily as print resources for individual users, basically your traditional print dictionaries. And their online interfaces, if they exist, will use old editions. There are some good quality resources that are designed for licensing, and maybe they're edited with the help of community volunteers. However, their offerings are subject to change. For example, They may remove a free online dictionary interface designed for individual users. Datasets that have an unclear license also pose a challenge. There's a project at U Chicago called the Digital Dictionaries of South Asia, and its purpose is to digitize all available dictionaries of South Asian languages. Now, some dictionary datasets do not have explicitly declared licenses, and this alone is a no-go for some companies because the license is treated as if it's proprietary, but without any sort of indication of whether and how those datasets might be used. There are other ways in which the legal environment can be uncertain. For example, there might be copyright laws in a country that stipulate a public domain horizon. In other words, after a written work has been published, they retain the copyright until 60 years after the author's death, for example, after which the written work goes into the public domain and anybody can use it in any way. However, getting an official government rubber stamp approval to verify that, yes, this written work is now in the public domain can be very difficult. Also, the provenance of data for smaller websites and datasets can be unclear. For example, GitHub is a website on the internet for openly sharing freely available open source information, and they'll be tagged sometimes with an open source license, but that doesn't remove the question just because they're tagged. And then there's an ethical question of who owns a dataset of the words of a language and at what point. Does it belong to some publisher, to the speakers of the language, or to everyone? Now, here's a screenshot of an actual dataset repository on GitHub, and here's what's written in the license. Who owns the nouns of a language? The creators of the dictionary or the speakers, writers of the language? We collected these nouns from the internet. We believe that all words in all languages are in the public domain. Enjoy, build better worlds with open source language computing tools. Open source licenses exist to protect the full and free access to code and data. Some open source licenses allow a fully unrestricted use, and they basically say something to the effect that here's some code and or data, use it completely as you wish, we take no responsibilities. Examples of licenses like this are Apache 2, MIT, BSD, Eclipse Public License, and Creative Commons Zero, which is effectively a public domain style license. The Unicode license fits in this category as well. There are other open source licenses that are less permissive, and that's because they place certain restrictions, such as whether you must publish any changes that you make or any derivatives of the work that you might make. They also might place restrictions on whether you publish code that touches any of the code or data that's under the less permissive license. So many companies tend to steer away from these. Examples of licenses in this category are the GNU Public License, Creative Commons Attribution Share Alike, and others. And Wiktionary, for example, uses a license under this category. Using code and data under the less permissive licenses can get tricky because the restrictions that they place take precedence over the boundaries of some of the code and data that touches it, even under more permissive licenses. So for example, if you have code and data under very permissive use as you like licenses, and they come in contact with licenses with more restrictions, the ones with more restrictions apply to everything. Or even in cases when that's not true, there's enough uncertainty and risk in commercial settings for them to be avoided. Then there can be a confusion among open source licenses. For example, the Tamil Nadu state government had an open source licensing policy for books under their nationalized books designation. Now, first, they declared these books to be under the Creative Commons public domain license. And then in the very next year, they changed the license to a less permissive license. And then there's the question of what if the licenses conflict with works that belong in the public domain? And by belong, I mean that legally stipulated, the copyright laws say that a certain work should be in the public domain. So if there's a publisher of a dictionary and that dictionary has gone into the public domain, but then the publisher is releasing that same dictionary under a somewhat less permissive license, then what do you do? To summarize the challenges of existing data sets, the first question that we have to answer is, do the data exist? Is there at least some data set in existence? And if there is, does it contain enough words that we need? Does it have other information like parts of speech tagging and bilingual data? And is the quality good? Is it vetted by people who know what they're doing? Then the next question we have to answer is, can I use it? Can I even access or download the data? And if I can, am I legally permitted to do so? Can I do so at least in open source applications of a certain type? And then after that, will commercial entities be willing to use the data, or at least in some derivative form? Given the challenges and pitfalls of using existing datasets, I decided to derive a lexical dataset for Thumr from scratch. What I wanted in my lexical dataset would be noun stems and verb stems, but I also wanted the verb stems to include a notion of a verb class as defined by Dr. Grau. And those verb class designations indicate not just how to conjugate exactly, but it also helps disambiguate multiple senses for the same verb root. The source of input data I used was from the Unilex project. So the Unilex project has words and frequencies of those words per locale. That data is under the Unicode license, and it's available in the Unicode umbrella of code on GitHub. The code and the data that was output from the code, I put back into the Unilex project in the root data stems TA, and TA is the locale for Thumr. My high-level approach to deriving the lexical dataset was to read in all the words, detect the verbs, stem them, and remove them from the original set, and then detect nouns and stem those. For detecting verbs, I created functions to perform verb conjugation. After having those functions, then I would try to find words that would match patterns of conjugation. And then after that, I could record the verb roots. So for example, in my word set, if I have the words irluduhirein, irludinain, irluduvein, which are the present, past, and future tenses of irludu, to write, then I know my verb root, and I also know that it belongs in verb class 3. When doing this, I also need to throw out false positives, say if the verb stem looks wrong for some reason, or if the verb class is incorrect. Then, when I have my set of verbs, I want to collapse multiple verbs that are forms of the same stem to just the single stem. So when I have irdu to write, I want to also combine that with the reflexive form and the continuous form and other forms so that I just am left with write, irdu. Then, once I have a clean set of verb stems, then I can use my rules of conjugation to thoroughly remove all different conjugations of all the forms of the verbs from the original word list. Once I've removed all the verbs, then I can detect and stem the nouns in the same manner. In order to implement the code to do the derivation, I needed to know some aspects of linguistics. So first, I needed to have some knowledge of the morphological rules, and this relates to the agglutinative grammar of Thumr. I used the lessons that I wrote at learnthumr.com, and the type of morphological rules include sandhi rules, which are basic rules for when words join together, like the intervocalic letters that are inserted when you add suffixes, as well as verb conjugation rules and noun inflection rules. Also, I needed to know how to decompose or break words into phonemes, and that relates to the abugida script being used. So this type of functionality is not provided by ICU currently. ICU does have break iterator, which will take input text and break it into sentences, lines, words, and characters, which are grapheme clusters. And there's normalization for Hangul to turn it into jamo. Now, for Tamil, the inspiration comes from Korean. Japanese and Korean have similarities with Tamil language in a few ways, but the script for Korean is the salient aspect here. Now, let's take a look at what it means to take abugida scripts and break them into phonemes. For people who are well versed in writing systems in Unicode, they're also well versed in the low-level computer concerns for languages, so they understand how scripts get represented in technology, using things like code points, encodings, properties, and font renderers. And what linguists would call letters, they might call grapheme clusters. So I want to contrast grapheme clusters, or the letters, with the phonemes to illustrate how the phonemes might be more appropriate. So let's take a look at the present tense conjugation of to write. So we have the sentence I write, and here we have the verb root, and to it we're adding the tense suffix, which is in blue, and we have the subject agreement, person, number, gender suffix, which is in red. So the phonemes provide the right granularity to represent that information. Whereas if you look at the grapheme clusters, there's an overlap in that information, which is indicated in purple. Now, if we just look at the phonemes and we look at it for the present, the past, and the future tense, we can start to see the patterns emerge. We can clearly see where the tense marker is and what they are, and we can also see that subject agreement, person, number, gender suffix consistent all the way throughout in red. In comparison, the grapheme cluster versions have a lot of overlap that obscures this relationship. Finally, let's discuss some implications of the things that we've seen so far. When it comes to dataset licensing, the status quo isn't all that great. Some of the best datasets are geared towards companies and entities with the most resources, and that's if the datasets exist and are easily accessible. But this leaves out everybody else. If the datasets are open source, they might be under licenses that place restrictions in ways that most companies won't use. And some of the biggest companies can be the biggest providers of internationalized services, and this ultimately impacts users. Wikidata, which is under a Creative Commons Zero public domain license, might be one place to consider putting structured ontologies of lexical data. Now, it's important to note that Wikidata is not the same as Wiktionary and Wikipedia, which have less permissive open source licenses. For the effort of deriving lexical data sets, it's important to consider the scalability of the whole process. First, it requires linguistic understanding of the language. So that knowledge should be in a form that can be easily converted to code. Now, it helps that I wrote the grammar lessons from the website that I used to implement my code, and it also helps that I prefer a style of grammar lessons that uses mathematical rules, because then it was very conducive to converting those rules into program code. It also requires a bit of technical knowledge. For example, you need to be comfortable with navigating a prefix tree data structure. And going back to the linguistic understanding, knowing whether to use letters or phonemes in the prefix tree is important. I also use zippers for functional programming style navigation of trees, and the zippers provide a few benefits, including the ability to navigate up, down, left, right within the tree, which was useful for matching the patterns of verb conjugation and noun inflection. It also requires a manual review process for false positives that result. So, in short, this is not a very scalable process, and it may not even be feasible, let alone affordable, for all of the unserved and underserved languages. But if you are embarking on this project to derive lexical data from scratch, then writing some code might be more efficient than a very manual effort. One way to think about phonemes for abugida scripts is that, in a way, they're sort of like an alphabet for alphabetic scripts. Instead of the full space of 247 letters, we can think of just the 30 phonemes for Thumber. So here, we would have the phonemes e, il, u, it, ki, and so on. So in this analogy, letters to an alphabet are like phonemes to an abugida. And grapheme clusters don't quite work the same way. They're not as useful. Because in this analogy, using grapheme clusters for abugidas is sort of like trying to make sense of English only using syllables. So for the word pre-recorded, we can see PRE is the prefix, record is the root, and ED indicates the past tense. But if I were to just use syllables, and if I could only look at the word in terms of syllables, I would have pre, re, core, dead. And that isn't quite useful, and there's an overlap of information. So in English, it's easy to gloss over the fact that a letter usually corresponds to a distinct sound. But even when we look at grammatical things as simple as plurals, or whether to use the word a or an as an article, depends on the phonemic values. It depends on the sounds, not the letters. For example, we need to know the ending sound for plurals, and we need to know the beginning sound of the next word for a or an. And put another way, we wouldn't be able to do a lot of natural language processing for English if we were restricted to the granularity of syllables when we were looking at our input text. There are some ideas that apply to all languages with abugida scripts, and Korean Hangul can provide inspiration. This is because abugidas and Hangul can normalize into phonemes. This normalization into phonemes is really useful, for example, in text indexing, because for sure, Korean search engines apply a normalization process as the first step of text indexing. And in general, this normalization can be useful for any text natural language processing operation. When it comes to applying machine learning for natural language processing, some of the algorithms might perform better if we use phoneme embeddings instead of other letter embeddings. And this is also potentially useful when we consider the presence of low-level details like zero-width joiners and zero-width non-joiners in some of the South Asian scripts, for example, that can complicate some of the algorithms. Another area where phonemes can be useful for abugidas could be in input methods. Here's a screenshot of a Korean input method where all the keys are the individual jamo. Now, here's an instance of a thumbnail input method, and the image on the left shows the key press of the la key indicated in the small circle, and the image on the right shows the result. Now, there are two things that are problematic in this scenario. The first is what happens to the vowel keys indicated in blue on the left-hand image. When the consonant la is pressed, then all of the vowels then turn into consonant vowel combinations. So a turns into la, i turns into li, and so on. But then on the next key press, no matter what it is, those blue keys will then change once again, and this causes a flickering. There's another problem too, which is that when we look at the vowels and how they change to the consonant vowel combinations, a changes to la, i changes to li, and so on. So there's a pattern. But in the very first position, the short sound actually changes to the pure consonant il. So that actually breaks the pattern. And the problem is that the consonant keys are actually not consonants. They're actually the consonant plus the short combination. So we have ka, nga, cha, and so on, and we're pressing the la key. But really what we want would be to have the pure consonants. So we would have ik, ing, ich, and so on, and we would be pressing the il key. And if we have a keyboard like that, with just the vowels and the pure consonants, then what we end up with is a keyboard of phonemes. And that matches actually the Korean keyboard because the jamo are the phonemes of the language. And in the Korean keyboard, all the keys are static. So this has simple, non-flickering keys. So to wrap up, here are links to some of the things I mentioned in the talk. Thank you for listening. And if you have any questions, I'd be happy to answer them.